Okay. All right, guys. So today we'll be looking at rotational motion with torque lab. I'm going to do a demonstration of this lab, and I'm going to show you how we can calculate both experimentally and theoretically the moment of inertia of a given object. Now, I have a question to ask you guys right off the get-go, and that is, if I were spinning in space and I were to remove all of the planets and all of the stars and any visible notice of any signs of matter, and you were to be spinning in space, would you know that you were spinning? If you could not see any stars or anything at all? You know, most of you shaking your head no, so the consensus is no? Okay. You would know you were spinning in space, all right? Because if you were spinning in space, your arms would fling out to the side. You would feel a centripetal force from the center of where you're spinning, all right? That is one of the fundamental properties that comes with inertia, all right? Inertia, which is Newton's second laws are based off of, well, all Newton's laws are based off of, is the idea that matter doesn't want to move from wherever it is relative to space itself. So even if you're in a vacuum of space, it still has some sort of entangled relationship with this vacuum. Okay, we know that because it won't act the same way if I start to spin it in that region of space. All right, even if there's no way to tell it's spinning. So that's one of the interesting properties that might not be as intuitive to you guys at this level. But so what we're going to do is we're going to calculate what is known as the moment of inertia, which talks about how an object is spinning around a central point. And you can calculate the moment of inertia for various objects just by simply, you can theoretically calculate the moment of inertia by simply using some sort of composition of the formulas for moment of inertia. Now, technically, in real physics, you integrate over a mass from a given radial point where it's, you know, where it's rotating from. So if I had some sort of weird object, which I make you do in graduate level physics, all right, basically, you can break this object into two objects, and you can say, you can calculate by integrating over space the moment of inertia of this chunk oscillating around a central point, and you can calculate the moment of inertia of a rod oscillating around a center point, and then use the composition of the two, simply sum together, you will figure out the total moment of inertia for any complex object. So that's what we're going to do here. We have this kind of dumbbell-shaped object, and we're going to spin it around a central point, and it has its moment of inertia. It has its moment of inertia, and we're going to calculate it theoretically, and we're going to solve for it experimentally, and hopefully the values come out the same. So we have 12 grams of the wing nuts, at which, actually I'll do that once I state.
63.
63, that seems right. Okay, so the mass of the rod is 63 grams. Okay, our rod. So it's important I tell you about the theoretical, okay? So I'm going to give you these formulas. You can look them up because in any physics textbook we'll have tables of the moment of inertia for various objects. So we're using a composition of two objects, a rod spinning around a central point, and then two point masses, two chunk masses spinning around the central point, all right? So all I have to do is just add up the total moment of inertia of all those contributions. The first contribution for a rod is 112 m rod L rod squared, and then the second contribution, now point mass spinning around a central point has a moment of inertia of mr squared. The units are meters, the units are gram meters per second, or gram meters squared, all right, no per second. So it is m weight plus wing nut, and then R, we'll call it R rod for the radius. I should call it, excuse me, I'm going to call this R weight to make it simpler. R weight. So R weight, and that's squared. And there's two of them. There's a contribution from one on each side, so I simply multiply that by 2. All right? And that is the total equation to figure out the theoretical value. So we'll plug in values and we'll figure that out before we even do an experiment. So M rod was 63 grams. And that's another thing you might have noticed marked off on your lab reports is that if you did gram meter per second squared and then called it in Newton, I didn't take off for it, but I made sure to put a red mark through it so you know. If you listed 2,000 newtons, if you want to entertain yourself and see why it's kind of funny to a physicist, look up the conversion for 2,000 newtons. All right, it's a very huge force. So it's kind of silly, you write down 2,000 newtons, at least that's newtons. But, length of the rod, so I'll measure the overall length of the rod, we need that value. So measure from here to here, it looks like about 34. So 34, 0.34 meters. And then the radius of the weight, we gotta measure how far out the weights are. Now, I can treat the weights as if they are the center of mass points at a given radial value. And that, if you have questions about it, I can explain later. But for all intents and purposes, if you were somebody right here and you could detect the moment of inertia of this object, you wouldn't know if this was a giant sphere or if it was a tiny marble, if it had the same exact weight, all right? To the person at the center, they wouldn't know the difference, not looking, okay? And that has to do with symmetry in physics. So we have what looks to be, I would call it, to be precise, I'll call it 15 point, well, I'll call it 16. So 0.16. Okay, notice that this isn't half of this, okay, and the reason why is because technically I'm not measuring from the center to the end point, I'm measuring to where the center of mass of this, this weight is. So, all right, so now we can plug into this equation because we have all the values we need. Length of the rod is 0.34, and get your calculators ready. Meters, and that's squared, plus 2 times the mass of a weight and the mass of a wing nuts on each end. So the mass of the wing nuts for 2 of them is 12, and the mass of the weight, these are 200 gram weights. So this is 212. And then the radius of the weight is 0.16 meters, and that value is squared. All right, so we need to figure out what this total value is, and once we have it, so one of the things you're going to need to do is you're going to need to stand on your pride and call out what you think the right answer is, and risk the idea that you might have the wrong answer because somebody else might correct you, but don't be afraid. We all make mistakes. I could get the wrong answer on a calculator, especially now because I don't use them anymore. So. I'm thinking it's in the 10.5 to 11.5 range.
I got 11.4613.
11.4613. 11.4613. Good with that value? Okay, very good. Usually I don't write that many sig figs. So what are the units? We have grams times meters squared, right? So those are the units for the moment of inertia, gram meters squared. And all you need to remember the units is that its simplest form, an object spinning around a center of mass, or spinning around a central point, has a moment of inertia by itself of mr squared. All right, so when you have mass times radius squared, you get gram meter squared if you leave it in grams, or kilogram meter squared. So this is I theoretical. Now one thing to big notice is that I call it theoretical. Technically, there are a bunch of measurements here, okay? But the idea is that if I was doing this experiment, the more variables would be taken from the experimental side, which I'm going to show you. These values, these measurements would be done very precisely, which I'm sure I just did very precisely. But precise enough, okay, so you get the point. All right, so we will investigate I experimental for an applied mass of M applied, spell applied, APP, LAD, and then we'll do 150 grams, 250 grams, and 450 grams. I'm going to wound this object up. So here's another value that's going to be important you're going to need for the calculations. That is the radius of this shaft. So I should explain what the top equation means. All right, I'm going to check the linear value of acceleration by winding this up and then suspending the hanger over the edge and letting it fall roughly half a meter. So I have this set up in such a way that when it's extended all the way to the bottom, this touches the ground, okay? I'm going to bring it up half a meter off the ground, and I'm going to let it fall. As it falls, it's going to unwind and unravel this shaft, okay? It's applying a torque to this object. Torque is radius crossed with the direction. Radius crossed with the direction of force, okay? So, most of you are familiar with wrenches, okay? If you want to apply a torque to a wrench, you're turning it clockwise, and you move outward from the center, right? So you're turning it this way, and you're always at a right angle, right? The torque is at right angles. And that's what happens here. This thing is going to spin this way, and I'm pulling it outward at a right angle always, okay? So I'm applying a torque to the system. From that, when you know the torque, if you know the angular acceleration alpha, then you can calculate the moment of inertia I, because torque is equal to I times alpha. All right, so we can actually use that to calculate it, and we'll get alpha from the linear acceleration, because a linear divided by the radius gives you alpha. Okay, so you can just trust me on that. But you can see here. So if I say I experimental is equal to the torque divided by alpha, then the radius of the shaft times the applied force, which will just be the mass on the hanger, times gravity, divided by a linear, which we'll calculate, divided by the radius of the shaft. Then if I rearrange it, when you divide by a fraction, you flip the fraction and multiply, so I move the radius of the shaft up here, and this is the overall equation. So you see I've derived the equation to only include the mass we apply, gravity, the radius of the shaft, and the linear acceleration, which we're going to calculate in each case. Now our shaft has been measured, and it's equal to 0.625 centimeters, which is equal to 0.00625 meters. All right, so that's an important value that we're going to use in our calculations coming up here. All right, so we'll do the first one. We'll measure the first one. All right, so I want to measure half a meter distance. The reason I'm measuring half a meter distance is to make it super easy in the calculation, because if you look, this is 2d over t squared. So as we did before in one of the other labs, 2d is just simply 1 meter, right? So I'll make it easy for myself by just measuring half a meter. So we'll get it down to here, and a bit lower. That's about half a meter right there. So I'm going to apply hopefully 100 grams. So I have a total of 150 grams. And I'm going to measure the time it takes to fall half a meter. Now the trickiest part in this is that when you first start it, it takes a second to start up, okay? And that's because this thing has friction in it, all right? Have you guys learned about friction, the difference between kinetic and static friction? All right, if you think about pushing a box across the floor, it takes more effort to start the box moving than it takes to keep the box moving, right? And that's the same thing for this device. It's going to have a frictional component, but from starting from rest, it's going to be slower to move. Then once it starts going, it has less of a frictional component, which means it plays less of a factor. So what I'm trying to say is I'm going to let this move just a little bit before I start the stopwatch. I'm only covering a very small rotation, so I'm not deviating my values that much. You understand? Okay, if it was moving much faster, it'd be a problem. But because I'm only covering this short arc, it shouldn't be too much of an issue. All right, so half a meter. The way I have it set up, when it hits the ground, I'll know that's half a meter and I can stop it. 13.35. All right, I'm gonna let it keep winding. And I'm gonna do one more just to make sure it's consistent. If it's too spaced out, I might need to do a third one. Just depends. But it's important to make sure that whatever values you record and you claim to have, that they are repeatable. And that you can confidently say, yeah, I can do this in front of anybody. I wanted it the other way, so. So 13.35, we wrote that down, right? Much higher time, 15. Here's my problem. One of the times I wound it up and one of the times I wound it down. So let me recheck this here. Which was there. All right, let's try this one more time. 14.84. Maybe I'm wrong. All right, I gotta do one more with those. So 13.35, one of them was 15, and then 14.84. So let's see which one of these is an outlier. 14.84. You whisper louder than I talk.
Wait.
Alright, we gotta do one more here. Now what you should find is when you add more mass in the upcoming trials, that the timing gets more closely spaced. Now we don't have as much deviance. How much difference is that? I might have been half a rotational. No, that was right. That was right there. It looks to be half a meter or so. One more trial and then we'll use the average regardless. Notice it did wind it one way and then wind it another. $14.79. So yeah, I think the first one might have been off because the other one was what, like 15-ish, right? So we got 3 up by. Was it just 15? What did I say? Who said that? Was it 15?
It was just
15 that I said? I don't remember what I said, so. Yeah, I thought that was gonna be the outlier, but it turns out it was wrong. So we'll use the 2 upper values. What are they? 14? What are they? 14.84. So we'll see trial 1. 14.84, and what was the other one? 14.79, so averaging those two, we get what, 14.82, 14.82 we can use? Let's use 14.82. All right, now what we do is we'll plug into these equations and we'll solve for successively for the moment of inertia. So calculate A linear, number 1, which is equal to 1 divided by this time squared, which is 14.82 squared. And give me the value when someone has calculated that.
0.0046.
0.0046. Guys, if you want, I mean, it might be my preference, but everybody I know at my level does it. When you say a value, say the 0 before the decimal, 0 point, you know, because everybody does it though, so I don't know why. And that is, if you look, A linear is 1 meter divided by second squared, so that's meters per second squared. And then from there, we can calculate the moment of inertia theoretical, experimental, I1. And that is equal to, okay, so we'll plug in all these values, 150 grams times gravity, which is 9.81, times the radius of the shaft, which is 0.00625 meters, that's squared, and all of that is divided by the linear acceleration, which is 0.0046 meters per second squared. $12.48. Okay, well, we'll work with it. Is that what everybody, do we have a consensus? 12.48, okay. 48. Okay, so that is I1 experimental. Experimental 1. 12.48, and if you look at the units, we can check to make sure we did it right. This is an acceleration, gravity is also an acceleration, so the units from that cancel, and we're left with just grams meters squared, right? So grams times meters squared. So do a percent error for that, and percent error is going to be the absolute value of 12.48 minus 11.46. All divided by 11.46 times 100%. 8.89? All right, so 8.89% error on the first trial. So it's not bad. Typically what you should hypothesize is that as I increase the mass, this thing overcomes friction much faster, so friction doesn't pay as much of a part. The other thing too is that the timing intervals should be, there should be less fluctuation in the timing intervals, all right? So without going into detail about explaining it, if you take more and more times, the faster this thing's moving, you're starting and stopping the stopwatch quicker, and you should see less of a deviation. The slower this thing moves, the more perturbations, if you will, can occur. So, are we good with this? Because I'm going to erase the values. So write down the values. It's your last chance to get those. I'm going to have to at least erase those. All right. Looks like our half a meter, which is good because it starts out. You can tell it's consistent because it's always facing straight forward at that half meter. So knowing where exactly this is positioned helps us be more precise when we take the measurement. I'll release, let it go a little bit. .86. You might have stopped that a little early. Let's do another really quick one. .86 at 250. You got that number down? Oh, it's up. .73, so that's pretty consistent, I think. 10.86 and 10.73. So let's see here. We have 10.86 seconds and 10.73. And what's the average of that? It's going to be what? 7.9? 7.95. All right, we'll use 10.8. 10.8 seconds. So if we plug 10.8 seconds into here, what do we get for the acceleration? .0086. Get some head nods. 0.0086. Okay, very good. And then finally, we'll plug back into this equation, 0.0086 meters per second squared, and 250 grams. So that's all we have to change out of that last equation. And then calculate the moment of inertia. So that'll be I experimental 2.
11.14.
11.14, so it looks like we're getting closer. Agreement? Someone else calculate it? Now we get some head nods. Gram meter squared. Very good. All right, so 11.14% error is going to be absolute value of 11.14 minus 11.46. That's the absolute value of that. All divided by 11.46 times 100.
2.79%.
2.79? All right, very good. 2.79% error. Oh, might have a future in this business. So that's 200 gram mass. I'll add to it to make it a total of 450. Wind it up. Guys, just a heads up, I don't want to sign your books this week, just because I'm lazy. So I'll sign them next week when I'm going around the room. I'll sign off on these pages. When I'm going around the room and you're doing the vibrating string run. So I don't have to all pile up just to get out of here today. SCUs. Alright, so 50 centimeters. Time trial. Sucker's moving now. 7.77. 7.77. See, that's a trick. It's not half a meter the other way. Because of the fact that it stretches across that. We'll see what happens. Shouldn't be too much deviation. 7.7. Stopped it early, but 7.53. So I think 7.77 might have been closer because I stopped that on timing. I'm gonna do one more, just to be sure. I felt like that was early. Let's go fast enough here anyway. Go back the other direction. There. You guys are doing a good job. 7.76. So yeah, might have been a little early too, but 7.77, 7.76, right? So we use 7.76 because it's in the middle. 7.53 I think was early, based on what I felt. You stop that. So we got 7.76 seconds. Take that. By the way, if you guys want to know a cool trick, if you don't know that, you take this number and you square it, and then you press the -1 key, and that's the same as doing this, pushing 1 divided by all that. So. Or you can just raise that to the -2. It's the same thing also. Alinear when you got it. You guys must have it because you're not typing.
0.017160.
0.017.
0.017 meters per second squared. Plug that over into this equation. 0.017 meters per second squared, and have a total mass now of 450 grams. Crossed fingers.
10.97.
What is it?
10.97.
Further away. All right. 10.97.
I didn't get it yet.
No?
No, I was just asking if that's what you got.
Oh. Is that what we got? I'll wait for consensus. Change the mass, right?
Yeah.
10.14. I got 10.13.
I'll take those numbers. 10.13. All right. Why is my old? This is the second time in a row that the last one comes out. So 10.13.
I got 10.14
I
now.
got 10.14.
Yeah, but I fixed it.
Okay. Well, it really doesn't make me feel much better, but 10.1. Gram meters squared. Okay, so let's ask ourselves what the problem is here, all right? And I'll give you a little insight as to how a scientist would look at this. All right, so was I early or late on my time? All right. Early? Based on what you saw or based on what the equations tell you?
What I heard.
Well, you heard, right, because that's what I thought too, okay? Well, let's see if scientifically it makes sense. The value of the time should be higher. So if we look at this equation, if I was early, then I mark this value low. So if I increase this value, what essentially happens to this value? If this goes up, right, it means this value goes down. And if this value goes down, it means this value goes down. And if this value goes down, it means this whole value goes up. And we need this value to go up, correct? All right, so let's take a look one more time and see if I can take a measurement where I was a little bit early, just to support my hypothesis. That aggravates me, because that's gonna be a silly percent error. Well, it's gonna be like, 10.14 is 14 over 11, which is gonna be roughly larger than 10. It'll be 11%, it's not horrible, but
11.52.
yeah, thank you. Good looking out. Alright, half a meter. Let's see. I'm not gonna try to be biased here, so. I feel a little late, but that was 7.87. Alright, so if that 7.87 was a little bit late, let's run that number and see what we get. Alright, because this tells you a little something. So 7.87, I'm gonna square that and invert it. That's experiment 3. What do we get for the acceleration? 10, what
10.68.
is what you get for the overall answer?
Oh, yeah, sorry.
What is this answer?
0.016.
0.016.
0.01?
Yeah, sorry.
10.67.
10.67? Okay. So the second round, 10.68. So even though that felt a little bit late, you would then lead you to think that there might be something else that we possibly did wrong here. Now what could be wrong? Well, I mean, based on our other percent errors, you would think that there's something systematically wrong with the theoretical value. I mean, do you have a reason to believe that this one's wrong if it's right the other 2 times and then the third trial? But I tried an under and I tried an over as far as time trials, right? So what could it be? Well, I started with the same lag. Maybe I let it lag too much. I usually went like 1 second. This thing covers an arc of, maybe 20 degrees, 30 degrees before I start the timer, just to get it moving, right? But maybe I don't need to have as much of an arc, right? If I started earlier, what's gonna happen? Time's gonna go up. Does the time go up help our answer? Right? So these are just I'm just giving you guys some insight about how I would, as a scientist and as a theoretical physicist, would look at the situation and address the errors, all right? I'm only putting reason behind anything I try to justify. I didn't say, well, it could be friction. Could it be friction? Well, if there's not enough friction, if there's more friction, if I take away friction, it's going to move faster. If it moves faster, I'm going to get less of a time. Is that going to help my answer? So how would I argue then that friction is a main component of potential error? See what I'm doing here? All right, so that's all I wanted to really break down for you guys. So, yeah, we'll use this percentage error. Actually, we'll use 10.68. I actually should use an average between the two, but let's do 10.68 real quick. Figure out what that one is.
6.81.
6.81% error. Yeah, so something you can write about is that it could be noted that each trial calls for a lag in order to get the apparatus moving. But in the last case, it may not have necessarily been reasonable to let it lag that much. Pretty much should have let go of it and started it, because it's going to be a lot of force. It's going to overcome the friction, and it's going to start moving faster. So yeah, that's it. Bonus question is a fun one, and if you answer it off the top of your head, I mean, you might be able to. There's a good source online. I don't know if it's the one I showed it to you, but all you basically have to do is, did I show it to you last week where I came into the PowerPoint and I said, here's why we don't write why human error is in labs? I did that one? Okay, then let me ask you a different one. How would your mass change if you were to measure it on the moon? Now, measure it on the moon. Now, for some of you, you may already know right away the answer. But I'm gonna tell you right now, this is a 2-point question. So there are 2 possible answers. You have to bring a device with you to measure your mass on the moon. So think about that. That's a way you can earn the second bonus point if you already know the way it's gonna change immediately. Just a heads up, little bit of a tip. The moon's gravity is 1/6 that of Earth, okay? So maybe that helps a little bit, maybe it doesn't. But yeah, how would your mass change if you were to measure it on the moon? Are there any questions for me?
For our lab report, did you want us to use the 10.68?
Use the 10.68 and they say, you know, maybe mention in passing, it should be noted that this was a time that appeared to be a little bit lagged, a later time trial, but really there was a delay in starting, so it could have been closer to the right answer. Other questions? All right, guys.